Okay. What I would like to talk about is a brief summary of Zieliński and my work. The main result is a framework procedure that allows to design a behavior for certain class of multi-agent system, design behavior for elements of multi-agent system. Okay, what I mean by designing the behavior is creating a schedule that assigns actions to be performed by the elements of the system in a specific amount of time. Okay, why do I even talk about this? First, the current design methods require a moderate amount of knowledge, domain-specific knowledge, that depends on the field that the method was inspired by. The inspiration comes from currently, the domain that inspires current method ranges from physics, biology, to control theory. What's even worse, the knowledge is not only required from the designer, but also from the stakeholder. So it's quite a challenge. Well, each project is different. What I mean by this is that if two projects differ in the used method, the knowledge, the experience gained from the first one may not help with the other one. Well, current methods usually require involvement from the designer at each design stage. Well, even if we make everything by the book, it does not necessarily work as intended by the stakeholder. And the last thing is most, if not almost all of the methods do not take under consideration functional requirements, not to mention non-functional requirements for and scaling of the project. Our method, our framework, differs that it only requires to know the basics of the V-graphs to use it. What are V-graphs? I will talk in a minute. It is highly automated. What I mean is that after one of the first stages, the design process can be left to specialized tools. And what is very important for us, it was very important for us, is that scaling and taking under consideration requirements is built in the framework. Okay, it's a very brief introduction without any formal notation to V-graphs. V-graphs are quite new language published by Robin Milner in 2008 to design systems with where both structural placement and interconnection between elements takes an important role. It's a nice feature, but all structures that can be expressed with this language may be represented visually. It allows for formal decomposition to bigger graphs and decomposition into smaller ones. And using structures called reaction rules, we can describe the dynamics of the system. Okay, formally, a big graph consists of the pair place graph and a link graph. A place graph consists of roots, nodes or vertices, and sides. the connections between elements represent the structural placements and name place graph between elements. Okay, the second element of every graph is link graph. It's a hypergraph that connects without direction, that links elements with connections without direction. This is a result of composing two previous elements. Okay, this is a very brief overview of our framework. I will try to briefly talk about each of the stage. I would like to emphasize that after the second stage, this grouping task elements, we can leave the procedure of designing the behavior into the specialized tools. We have also developed a proof of concept set of software to demonstrate it. Okay, defining the task. For an example that I will use to cover the design framework, I will use the very basic task. Well, this is an example. We consider two UAVs, two drones that are placed in the same area. We call it area of type A, and the goal is to move them to an adjacent area of type B. Very simple. But even on this example, we can demonstrate both cooperative actions and independent actions that may be performed by elements of the system. The UAVs are capable of moving up. What we want to emphasize with the verbal definition of the task is that all we need is defining an initial state, what we have at the beginning of at the start of how the system starts, let's say, and capabilities of each element. In this case, there are two ways that UAVs may move. They can move between areas independently or moving together. Defining task using the bigger language, like I said, consists of describing an initial state and set of reaction rules. In this case, this is the graphical representation of all the initial states of the initial state for the system described earlier. Like I said, there are two types of areas. We say A and B, and two indistinguishable UAVs. This now describe that I used to describe vertex with control U. Set of actions. Based on the verbal definition, we can distinguish two reaction rules. The R1, let's say, but it can be named in any way. The reaction rule R1 represents moving independently each UAV. The L2 reaction rule is meant to represent moving them in cooperative manner. Okay, this is a graphical representation of the first reaction rule. The sites in this reaction rule represent that there might be these are patterns that the left-hand side is called redux, and the right-hand side is called reactor. The left-hand side both sides actually have sides to them, and they are meant. These are patterns that are tried to be found in each state of the system. The sides in this pattern mean that there can be absolutely anything, including nothing, in a big graph that this pattern may be found. So, for example, there might be an UAV in area A or in area B. If, even though we know that it is impossible, the pattern will be matched with a situation where a UAV or multiple UAVs will be stationed in the both areas. Okay, this is a graphical representation of the second reaction rule. Okay, the second stage is grouping task elements. We can distinguish three types of elements: an environment element, passive objects, and active objects. The first group consists of elements, task elements that are important in some way to task execution, that we do not take under consideration time for them, and they cannot initialize any action. Passive objects are ones that the time is important for them, but they may not initialize any action. And finally, active objects in multi-agent system terminology, they are agents. They are the time is both time, and the time is important, and they may initialize actions. Okay, the next step is to construct tracking graphical reactive system. This step might be automatically generated based on the set of reactional and the initial state. Tracking the graphical reactive system consists of a set of B-graphs and a set of reaction rules. Moreover, we can define a reaction relation over any tracking the graphical reactive system. This is an example of tracking the graphical reactive system for the system defined for the task defined earlier. What we can see read from this tracking TBRS is that action independent moving may occur in system. Oh, what is important? At this stage, the time is not taken. It's not considered. The flow of time is not considered for any action. What we can see is that reaction R1 may be performed in two states. That is B0 and B1. Their graphical representation is listed on the right, and the action represented by L2 reaction rule may only happen from the B0 state of the system, which is quite intuitive because only both B-graphs can only move to B when they are at the A area of type A. Okay, tracking transition system. Any tracking the graphical reactive system can be transformed. Oh, and at this stage, we do not distinguish between different instances of the same type of activity. Tracking transition system consists of a set of B-graphs and a set of transitions. This is the tracking transition system for the system described in this example. It resembles the graphical system from the previous slide, and the difference is actually there's besides the two functions participate and residue function, the most significant difference between those two structures, I mean, the graphical reactive system and tracking transition system, is that this structure distinguishes between different instances of the same type of activities. What I mean by this is that from the B0 state, each of the UAVs can move, can initialize the movement. That's why there are two arcs from B0 to B1. The function, power function, which is an acronym for participation function, points which element of the input system takes which role in the regex of the reaction loop that is represented by each transition. The residue function, on the other hand, allows us to track elements between different states of the system. Okay, state space. Having any tracking transition system, we can reduce it to a directed multigraph with structures called mission progress function assigned to each arc. This is the first time when we take time required to perform each action under consideration. This is a graphical representation of state space for the system described in this example. Just for the record, definitions of these functions looks like this, but they want to this is just for the record to emphasize that each of these functions is very easy to compute. The first argument is an element of set called cursors, of possible cursors of the mission, and the second one is time, the length of which activity we take under consideration. Okay, finally, if we define behavior policy as a wall in graph theory sense in state space, we can describe a collective behavior consisting of atomic interactions between elements of the system from the initial state to the one of the, let's say, satisfactory states in the state space as something that we would like to convert to schedule of actions. Schedule of actions. If we can find such a walk from the initial state to the destination state, then we are almost good. Almost because the conversion between behavior policy and schedule of action is not trivial. It's not trivial. Okay, one of the results of our work is an algorithm to find all walks. For those of you that are into graph theory, we designed an algorithm to find all existing walks in a single iteration in directed multigraphs. I will skip the formalities, but the algorithm is based on two types of matrices. The first one is a matrix of possible progression of the changes in the system. Each element it very much resembles the adjacency matrix for a graph, but the difference is that instead of binary values in this matrix, we take each element of this matrix is a finite series, finite function series with functions belonging to a set of mission progress functions. The second type of matrix is mission of known cursors, that is, mission of known cursors of the mission at a specific moment of time. For this task, with two UAVs, the initial there's only one known curse leading to initial state that requires no actions, and we assume that both UAVs starting at the same moment of time, so zeros. Anyway, if you really find multiplying such matrices that multiply and elements of such matrices is equal to convolution of series being the element of each matrix, then each iteration of each multiplication in result gives us every possible walk of a given length that lead to all states in the system. For example, there are no walks of the length 1 consisting of one arc in the state space from the initial state, that is 0, to the same state. That's because we do not have loops in this stage. But there are two walks of the same length, that is consisting of one arc, that can lead us from state 0 to state 1 and to state 1. And finally, there's only one walk from state 0 to state 2. I will skip this slide. And finally, the last stage of the framework is converting a behavior policy of a valid system, of the valid model, to a schedule of actions. These are two examples converted from this walk. They assign which role take each element of the system. Okay, as a summary, there are the biggest downsides of the framework in its current state is that it is required to consist of a constant number of objects. That is, elements that we take time under consideration for. And all agents must be controlled. That is, we do not allow, let's say, people that may do as they wish in the system. The most important features, in our opinion, is that scalability of the projects is included both vertically, including during the design process, including additional stages, and expanding the system by increasing number of elements in the system, and verifying functional requirements is inherent to the design stage, but non-functional requirements are also possible at different stage elements, but it very much depends on the kind of the requirement. And thank you.
Thank you. I have a small question. In these systems, the main problem is navigation. Navigation for SWORD and individual element of SWORD. Do you get into consideration in your solution this problem?
Yes, but first of all, yes. The shortest answer is yes. But I would like to emphasize that the coordination is not the biggest problem in this kind of systems, because if we only consider swarms that are meant to move from one point to another, then yes, absolutely yes. The biggest problem is how to coordinate them in, let's say, cooperative or independent manner. But if the swarm, the design swarm, is designed to, for example, pick some objects on the map, or at some point of the task execution of the given task, they need to connect to each other or to some beacons on the map. Then synchronization and coordination is. I wouldn't agree that in such tasks, coordination is the number one problem that we need to face. But yes, this framework.
Yes, but the basic of navigation today is a GPS system. Yes, but when you don't have the system, how the drones, for instance, going to the target?
Well, there are a number of solutions that I may suggest, but what I would do at the ad hoc manner is, for example, make the map discrete, and the schedule of actions forces swarm elements to
go for one leader, yes?
No,
No.
each element is forced by the schedule of actions to move to specified area that the important thing is that we need to know the area before the map starts. So the reconnaissance, in the sense that we do not know where the swarm is coming, is not an applicable mission type for this framework right now, at least. But if we know the map, then we can, without GPS, force based on the, let's say, the usage of the motors of each drone, we can force each element of the swarm to move, to coordinate. Yes. Mm-hmm.
I'm not sure, but thank you for your answer.
I have a question. Because this is only a formal description, yes? When we can see the results of the simulation implementation of the system with different assumption conditions, sometimes with unacceptable situation for simulations.
So for the simulation part of the question, there is currently simulation prepared to visualize how a task may be performed. But I didn't include this in the presentation for two reasons. First of all, the task, the visualization of this task would be so trivial that would not help anyone to. It's as good as seeing schedule of actions or two states of the system. But the simulation is ready. As long same thing as a set of tools to generate schedules of actions. Yeah, the simulator is ready. The unexpected about the unexpected events during the mission. This is one of the constraints that I've said, but all agents must be controlled, and we do not expect situations that like outside intervention in the system. So, for example, we can, with this framework, design behavior for a swarm or a multi-robot system that in the set warehouse has to, let's say, display some boxes. But this is a primary example of the use case for this framework, not an outside intervention from outside.
Yeah, that's good. So if you look at this is the formal way to represent a mission or something that you want the swarm to do, right?
Schedule, yes.
Yeah. Do you think, I don't know if this is part of your research, but do you think it's possible for this type of logic to go into some type of a specific language, like domain-specific language, where you could maybe create a tool that creates missions for drones, and in real life you can control them and demonstrate these segments? Or maybe that's part of your work, I don't know.
This this actually is a graphical representation of a formal structure. This isn't just me drawing something. But in my opinion, this is let's say, the second most easy to comprehend form of addressing which element of the system needs perform which role in which type of activity. I mean, by role, I mean this vertex of the radix. The second part of your question was if you can.
My thinking is this: so if I take this and I want to make it into mapping messages that I want to send to the drones.
Okay.
To control them. What is the process and how much work there is? I'm just interested.
It's totally automated. We have already created a set of tools that if you construct two structures, I mean specifically a set of fraction rules like this, and the initial stage in the form of big graph, then the rest you need to address the time required to perform each of the activities, and the rest is fully automated. You give it an input in the form of a big graph and a set of fraction rules. It's actually mentioned in the article migration. So it's fully automated.